Okay, so today's discussion session, cyanobacteria can see. This paper came out on Tuesday, and I couldn't resist. This is just a really interesting topic. It's like a lot of these really cool papers. It can get a little bit out of hand, a little bit overblown, but I think it's interesting all the same. And so the paper is here. You can take a look at it. I like the website because this video says it all. Cyanobacteria use micro-optics to sense light direction. Notice that they're not talking about creating and interpreting images. We're not talking about, whether these things need glasses if they're not quite round or anything like that, right? It's a light sensor, and it detects the direction the light's coming from. And it's actually been known for a while. See, most bacteria, when you think about the tumbling and running process that E. coli goes through, the way it determines where to go in a gradient of attractant or repellent is an integration over time, right? It is the concentration of glucose going up or down when I'm moving this direction. These organisms don't do that. They don't have to sense whether the intensity of light is going up or down as they move through the environment. They can see what direction the light's coming from and move directly in that direction. That's a big advantage, right? And it's been known for a long time that they could do this, but not how they could do it. I'll also point out that this has nothing to do with their mechanism of motility. So these things move by gliding. And that gliding, we'll talk about motility a little later. In this particular case, although most cyanobacteria that move by gliding, well, most cyanobacteria move by gliding, in most cases, that's a secretion of polysaccharide mechanism, where there are pits on the surface of the cell, and they secrete polysaccharide, and that saccharide hydrates and expands dramatically, and that it's like a little rocket engine, right? And it pushes it forward. This is not how these things move. These things move with pili. So what they do is, here's the cell. They push a pilus out. That pilus has an adhesive on it that grabs a hold of the surface, and then it contracts, and the cell moves in that direction. And they're constantly pushing out pili. And so they can actually move pretty smoothly because, if you've got 20 of these pili always grappling out and moving, it'll move in a more or less smooth fashion. But the mechanism of motility isn't the issue here. What the paper is about I'm going to push this thing out so I can draw on the board, is how this thing works like a little eye. So here's the cell, and in Synechococcus, the thylakoids are concentric around the perimeter of the cell. So these, they really are like thylakoids of a chloroplast, but instead of stacks of pancakes, they're around the perimeter of the cell. So if the light is coming from this direction, what happens to that light as it hits this round cell? Remember that the index of refraction of a cell is much higher than water. This is why phase contrast microscopes work. And so this thing is like a little lens. And so when the light hits it, if the light comes straight on, then it goes over here and it's hitting this part of the cell. But if the light is coming from over here, it will be bent. And the result is, just like your eye, you end up with a spot here, and somehow, here my hands go waving around in the air, somehow that signal is sent to the motility mechanism, which tells the cell to push pili out from this side of the cell for motility. Okay? And so light's coming from here. The signal is sensed on the opposite side of the cell. And as a result, the cell moves in that direction toward the light. Now, they're a little bit deceptive, in my opinion. Where's the... They have a picture. Maybe it's only in the paper itself. No, there's a... There's no image involved here. This is a great way to view it. And so the light comes from here, and this is the intensity of that, the focus of that light on the other side of the cell. Why is there no image? Why can't they see? Because this cell is about 3 microns in diameter, and the wavelengths of light we're talking about are about half a micron. And so there just isn't resolution. Just like you can't see anything much less than a micron in a microscope, in a light microscope, the wavelength of light limits the resolution of the image. And so these organisms could never, at least using normal optic methods, could never create a real image this way. And so the demonstration of this, the demonstration that this works is in this video. And so what they're doing here is that they've got a bunch of Synechococcus cells. They're looking at this in a phase contrast microscope, or dark field microscope, excuse me. And there is light coming from this direction. And so the cells are moving generally in this direction. But they have a laser spot right here. And what's going to happen is that the cells are going to touch that, and they're going to misinterpret the signal they see. And so if you have this cell here, and light's coming from this direction, and it's being focused on this point over here, the cells will move in that direction, right? Now what happens when they hit that laser pointer? So here's the laser spot. They're going to see the intensity of light here, and they're going to think the light's coming from this direction, right? And they're going to change direction and move that way. So you're looking for cells to bounce off of that laser pointer in the opposite direction. Let's watch. See, you see it? You bounce right back. Now that one, there he goes. And of course, there's too many of them, so they interact with each other. Oh, he's probably getting fried. I can't imagine what that does to the photopigments, by the way, the thylakoids. Now, as soon as they get away from the spot, they reverse and then start to move back in the other direction.
And that was real time.
That's real time.
That
That's real time, yeah. So let's do that again. Just and I'm going to zoom in if I can. I have no idea. There are ways to do that on a microscope with a mirror. We're going to talk a little bit later about a paper in which they use a laser like this, in which it's a infrared laser, so it's got longer wavelength, about the same size as the size of the cell, and you end up then with a set of optical tweezers. The cells get in that, and because they're in a trough in the laser light, they can't get back out again. So we have to capture a single cell and hold it there while you push off all the others, and then you can isolate out one organism. It's a really cool trick. But let's take a look at this video again. So watch it bounce right away. Isn't that cool? My guess is that there's not enough heat deposit in there to cook it. But I also guess is that you're bleaching all the photopigments in that region. And so what that does to the cell, I don't know. All right, so I'd like you guys to have a look at this paper. Think about what it means and come up with some kind of interesting question or something that you would pursue. If you were a grad student in this lab, what would you want to do with this information? Or more realistically, what would you already be doing with this information, right? You're already halfway down a project by the time this stuff gets published. So what's the resolution of this vision? If you've got light's coming from more than one direction, what happens? They talk a little bit about this in the paper. But is it relative intensity of light? Does it make a decision? What's it do with information more complicated than a single light source? You know that the key system is used to control motility in E. coli. It's an integrative system that runs off phosphorylation of some proteins, and it drives flagellar motor activity. What about this? Other kinds of motility are directed by the key system, gliding and so forth, and other bacteria. What about this? And how would you test it? What exactly are they looking for at the light? Notice that both the white light that they use to draw the organisms to motion work, but also that long wavelength red light also directed its activity. You suppose that maybe there's some wavelength specificity in this, or intensity specificity? Maybe there's a threshold. Maybe it becomes it doesn't look like too much light. It turned it into a repellent, so because it didn't pull in. So how do you think that the organisms might respond to different kinds of light? What other kinds of bacteria, or I suppose archaea, might use some kind of visual system like this, other than Synechococcus? This works because Synechococcus is a sphere, right? And presumably, if it was much bigger or smaller, it wouldn't work. Or maybe it would alter something about its index of refraction to make it work. But a filamentous organism couldn't do this, right? Or could it? Other things it could do. What other kinds of organisms might want to be photoattractant or photorepellent and could use systems like this? And how would you test that? So that's what I want you to do. I want you to think about this. I want you to talk amongst yourselves about what kind of interesting questions this raises, but not just any kind of questions, but the kind of questions where you can answer them. Something you could do an experiment and get some information. All right? Have at it. And don't forget to come back and talk about it later. We've got a couple of people who've already chimed in. I'm trying to respond as I can to these. There's some cool stuff going on with us.